Today we want to start looking at the atom, what is called the Standard Model. The atom is something we can't see or look at, and it's a little complicated. So I think the best way to see where we are at is to go back to the beginning and see where we came from and how we got here. Let's go back about 2,500 years to the ancient Greeks. Democritus of Abdera suggested the world is made up of only vacuum and atoms, an infinite number of tiny, hard, indestructible particles which combine in different ways to produce a variety of everything in the world, both living and non-living, which is surprisingly close to what we accept today. Unfortunately, there were other Greeks who believed differently, and those Greeks seem to have had much more influence than Democritus. But about 200 years ago, things started to change. People weren't satisfied with the old explanations, particularly when the old explanations didn't explain things that they were observing. Take Amedeo Avogadro, for example. He noticed that equal volumes of all gases at the same temperature and pressure contain the same number of particles. Avogadro figured that since balloons are kept inflated by collisions of particles moving around inside of them, and that the walls of the balloon, the higher the temperature, the more collisions. So if the gases were at the same temperature, they must contain the same number of particles. Around the same time as Avogadro, John Dalton noticed that when they mix chemicals together, they always mix in exactly the same proportions. He thought that this must be because the chemicals must be made up of the smallest little bit, sort of a lowest common denominator, if you will. Next comes Dmitry Mendeleev, who I hope you learned about and remember from chemistry. Mendeleev is responsible for the periodic table, which arranges elements in columns of similar properties. His periodic table had gaps in it. He predicted that elements would be found to fill these gaps, and they were. Our first direct physical evidence comes in 1897, when J.J. Thomson discovered the electron. This led Thomson to propose what he called the plum pudding model of the atom, or it's sort of a blob with electrons sprinkled evenly throughout it. Around the same time, there was another problem that was haunting physicists, and which you have done a lab on, the black body radiation problem. I bring it up now because the solution to the black body problem will be a puzzle piece in our solution to the structure of the atom. Black bodies are objects that absorb energy and then radiate the energy away. If you have ever put a piece of metal in a fire, you notice it glows red, and then orange, and then finally white hot. The metal was a black body. The color is related to the temperature. If it radiates, the more energy it absorbs, the more energy it'll radiate. So looking at this lava flow, you can tell the temperature by just observing its color. For instance, right here, that's about the temperature at that point, and the lava is about 800 Kelvin. Or right about here, the temperature there is about 3000 Kelvin. Same with this fire. If we look right here, we can tell the temperature there is about 1800 Kelvin. And if we look right about here, we can tell the temperature there is about 32 Kelvin. What's the temperature of the flame in this pizza oven? Right about here. Did you guess 32 Kelvin? 3200 Kelvin? The black body experiments were set up with hollow metal balls with peepholes in them. The balls were placed in furnaces and their color could be seen through the peephole for observation. The hotter the furnace, the metal balls became, the colors would go through red to orange to yellow to white. The problem was that no matter how hot they got the furnaces, the metal balls never would reach ultraviolet. The problem was actually referred to as the UV catastrophe. These are the curves they got, the blue, the green, and the red ones. The black is what they were expecting, but they never got it. A scientist named Max Planck came up with a solution that explains the black body radiation problem. He said light is carried in packets of energy called quanta. The energy of the light is directly related to its frequency. His formula for this is very simple. The E is equal to energy times N times H times F. The F is the frequency of the light. H is Planck's constant, which is 6.6 times 10 to the minus 34 joule seconds. It's a very small number. And the N is for the steps the energy must come in. In other words, everyone thought that if you put a little bit of energy into something, it was like going up a ramp. A little bit of energy, you moved up the ramp. A little more energy, you moved up the ramp. No matter how little energy you put in, you still managed to work your way up the ramp. Planck said, no, it wasn't like that at all. It's more like stair steps. You need enough energy to get to the next step. So you would go to another step, but a little bit of energy would not get you to the next step. You'd fall back down. So a little bit and you'd fall down, a little bit fall down. You had to have enough energy to get to the next step, enough to get to the next step, a little bit of energy and you fall back down. But it was even worse than that. The stairs got higher as you worked your way up. The other problem that was nagging physicists at the time was the photoelectric effect. You did a lab on this in another lesson. It was observed that when light strikes metal, electrons were released in the metal. In this picture, the blue rays are light and the little red balls are electrons. In 1905, Albert Einstein came up with an explanation for this phenomenon. By the way, 1905 is the year he proposed special relativity and also the year he explained Brownian motion. Einstein used Planck's idea of quanta, or particles of energy, that for light he referred to as photons. The photons strike the metal with enough force, it would dislodge the electrons. In this example, incoming blue light, which would have high energy, strikes the metal plate with enough force to dislodge the electrons from the metal and to give electrons enough energy to reach the opposite plate, and thus completing a circuit, and we have electricity flowing. In this example, red light, which has low energy, strikes the plate with enough force to dislodge the electrons, but it doesn't give them enough energy to reach the opposite plate, so we don't have flow, we don't have current or electricity flowing. Based on Planck's formula that energy equals Planck's constant times frequency, the frequency of each color determines how much energy it has. In this diagram, red is the lowest, next is green, and blue has the highest. The energy is transferred to the electrons, which gives the electrons kinetic energy equal to the energy of the light. Photodiodes are based on this principle and can be used to automatically open doors when someone walks in front of them, automatically turn on lights when it's dark, track packages on a conveyor belt, or determine when a camera needs to activate its flash unit because it's too dark for a picture. To summarize, Planck proposed energy is made up of packets of energy called quanta. He did this to explain black body radiation. Einstein, in regard to light, said the quanta are photons. He did this to explain the photoelectric effect. But wait, didn't we determine in the last unit on light that light is a wave? And doesn't this prove light is a particle? So which is it? It's both. Light is both a particle and a wave. Einstein put it seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do. We will see that this is the heart of the way the world is. But first, let's learn about Ernest Rutherford's experiment. You will be doing a lab similar to this. Rutherford used a piece of gold foil. You can see it here in the center. Gold foil is very, very thin. It's only a few atoms thick. He bombarded the foil with alpha particles here in this orange tube looking thing. By the way, alpha particles are radioactive particles, which we'll learn about on another day. For now, though, there are helium nuclei, 2 protons, no neutrons, no electrons, just the nucleus. Surrounding the gold foil is a fluorescent screen. You see it here in green. When an alpha particle hits it, it glows. Based on Thomson's plum pudding model, Rutherford expected the alpha particles to go straight through, but that's not what happened. Some of the particles went through, but some went sideways. Some even went back the way they came in. What Rutherford had discovered was that atoms were mainly empty space. That's why a lot of the alpha particles went straight through. But he deduced that the atom must have a dense, small, positively charged nucleus. That's what caused the deflections. He also used statistics to determine the actual size of the nucleus. Rutherford proposed a planetary model for the atom. In this model, electrons are like planets orbiting a central nucleus. But this had one big problem, and he knew it. Why don't the negative electrons fall into the positive nucleus? Also, scientists knew about atomic spectra, and any model should explain atomic spectra. This model didn't. So what do we have so far? We know about the electron. It's negative, and it happens some region outside of the atom. Planck and Einstein introduced the particle of energy called a quanta. In case you haven't guessed yet, that's going to lead us to quantum mechanics. And we know that the atom has a small, dense, positively charged nucleus. At this point, scientists were familiar with the atomic spectra, and they thought that any model of the atom should explain this. So let's review spectra. In the top picture, what that you have here is a glowing sample, some atomic sample that's putting out light. It's luminous, and the light is passed through a prism. A spectrum is produced, which is a series of colored lines, like this picture here in the center. This is called an emission spectrum. The bottom picture shows that if you have a gas sample and you shine a light through it, that's here, and you pass it through a prism, it produces a full spectrum with black lines in it, sort of the opposite. This is called an absorption spectrum. The spectrum of any element is like a fingerprint for that element. It is always the same. So it must have something to do with the atomic structure. But there's no obvious pattern from looking at the different spectrum of the different atoms. In 1913, Niels Bohr used Planck's quanta to explain the spectrum by explaining that the electrons are only allowed at certain specific energy levels. This is called Bohr's planetary model with stable orbits, and is very close to our current understanding. The spectra are electrons emitting energy. They only emit energy when moving from high levels back down to lower levels. And these levels are only in specific places, like the stair steps. In this example, we see that electron falling from the third level to the second level gives off red light and gives off blue-green light when going from the fourth level down to the second level, and gives off violet when going to the fifth level down to the second. Finally, why are Bohr's electron orbits stable, and why don't the electrons spiral into the nucleus? This is going to take some explaining, so bear with me. We start with Werner Heisenberg in 1927. Heisenberg develops the uncertainty principle, stating it's impossible to know both the exact position and the momentum of an electron. Here is a video showing you the uncertainty principle in action.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it could be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. Well, you see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. It makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit, so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty in momentum needs to go up. I should specify this is uncertainty in momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.
So we can't be certain about the Eklan. It's a good thing that Max Born introduced the idea of probability into quantum mechanics. So the location of these electrons levels are based on probability. As you see in this diagram over here, where you don't have clean lines for the energy levels, they're a little fuzzy. Here's an example of hydrogen, which just has one electron. This is the probability curve of where the electron could be found. It's most likely found at 0.053 nanometers from the nucleus, but there are other possibilities also. Our next contributor is Louis de Broglie, who proposed a revolutionary idea. Recall that we used to think light was a wave, but Planck and Einstein demonstrated that it's also a particle. De Broglie suggested that the electron, which we thought of as a particle, might also be a wave. Experimentally, electrons diffract just like light does. Finally, Erwin Schrödinger put it all together and developed the quantum mechanical model of the atom, and he produced the wave equation that lets us do calculations on it. Electrons are wave explained why the electron orbits are stable. They have to complete their wave, as in the diagram on the left, which shows a complete wave. It starts here and it's complete. The situation on the right is not allowed since the wave is broken. It doesn't complete itself. You follow that one. We trace it here. Notice here it's broken, it's not complete, it's not allowed. Here's another visualization of the same thing. If we think of the energy levels as these circles here with waves on them, and we take those waves and stretch them out flat, notice each energy level is stretched flat. So N1 is one wave, N2 is two waves, N3 is three waves, N4 is four waves. No fractional waves are allowed. Here's a summary for your notes. Pause if you need to. That's where we are today. This is Bohr-Einstein. Einstein objected to this explanation of quantum mechanics, which we refer to as the Copenhagen interpretation, because he felt it had no basis. Schrödinger also objected to it. Attempts have been made since then to try and find a basis, but everyone has also enjoyed the practical applications like semiconductors, lasers, and nuclear power to be too bothered by a basis for this.